What is an earthquake? An earthquake is a sudden release of energy in the Earth's crust that creates vibrations or seismic waves, which travel through the ground. These vibrations can be so faint they're detectable only by sensitive instruments, or so strong they topple buildings and reshape the landscape. The point inside the Earth where the energy is released is called the focus or hypocenter, while the spot directly above it on the surface is known as the epicenter. The closer you are to the epicenter, the stronger the shaking usually feels. Earthquakes can last just a few seconds or continue in pulses for minutes. Often, smaller tremors called foreshocks may occur before the main quake, and aftershocks can continue for days, weeks, or even months as the crust adjusts to the new stress distribution. Plate tectonics, the driving force. To understand why earthquakes happen, we need to look beneath the surface at the structure of our planet. The Earth's outer shell, called the lithosphere, is broken into large sections known as tectonic plates. These plates float slowly on a softer, partially molten layer beneath them called the asthenosphere. The plates move only a few centimeters per year, but over time their movements add up. Where they interact, sliding past each other, colliding, or pulling apart, the stress in the rocks can build to a breaking point. When that stress is suddenly released, it sends seismic waves radiating out from the fault line, causing an earthquake. There are three main types of plate boundaries associated with earthquakes. Transform boundaries, where plates slide horizontally past each other, like the San Andreas Fault in California. Convergent boundaries, where plates collide, often forming mountains and subduction zones, like the one that caused the 2011 Tohoku earthquake in Japan. Fault lines, the cracks that break. Most earthquakes occur along fault lines, which are fractures in the Earth's crust where movement occurs. Think of them as stress points where the rock has cracked and shifted. There are three primary types of faults. Strike-slip faults, where blocks of crust move horizontally past each other, typical of transform boundaries. Normal faults, where one block drops down relative to another, common in areas where the crust is stretching apart. Reverse or thrust faults, where one block is pushed up over another, usually at convergent boundaries where plates collide. When the stress along a fault overcomes the friction holding the rocks in place, the rocks suddenly slip, releasing accumulated energy. This abrupt movement is what we feel as an earthquake. Some faults, like the San Andreas Fault, are well known and monitored closely, but there are thousands of smaller faults worldwide that can still produce damaging quakes. Seismic waves. How the shaking travels. The energy released during an earthquake travels through the earth in the form of seismic waves, which are what cause the ground to shake. There are two main types, body waves and surface waves. Body waves travel through the interior of the earth and include P waves, primary waves, which are compressional and move the fastest, arriving first at seismic stations. They push and pull the ground in the direction the wave is traveling. S waves, secondary waves, which move more slowly and shake the ground side to side or up and down. Surface waves, as their name suggests, travel along the Earth's surface and usually cause the most damage during earthquakes. There are two main kinds, love waves, which move the ground side to side, and Rayleigh waves, which create a rolling motion, like waves on the ocean. The combination of these waves determines how intense the shaking feels at any given location. Measuring earthquakes. Scientists measure earthquakes using seismographs, instruments that detect and record ground vibrations. These records, called seismograms, show the arrival times and strengths of different seismic waves. The magnitude of an earthquake refers to the amount of energy released at the source. Historically, the Richter scale was used, but today seismologists prefer the moment magnitude scale, UW, which is more accurate for very large events. Each increase of one whole number on this scale represents about 32 times more energy released. The intensity of an earthquake, on the other hand, refers to how strong the shaking feels at a specific location and how much damage it causes. This is often described using the modified Mercalli intensity, MMI scale, which ranges from barely noticeable tremors to catastrophic destruction. By studying seismic data, scientists can also determine the depth of the earthquake's focus, the direction of fault movement, and even create maps showing how the shaking was distributed across regions. Earthquake hotspots around the world. Not all places are equally prone to earthquakes. The vast majority occur along plate boundaries. One of the most famous and active is the Ring of Fire, a horseshoe-shaped zone around the edges of the Pacific Ocean. This region includes countries like Japan, Indonesia, Chile, Mexico, and the western United States, all of which regularly experience strong earthquakes. Other hotspots include the Himalayan region, where the Indian plate collides with the Eurasian plate, and the East African Rift Zone, where the African plate is slowly splitting apart. Even areas far from plate boundaries can experience quakes. These intraplate earthquakes happen on ancient fault lines that can still be reactivated. A notable example is the 1811 to 1812 New Madrid earthquakes in the central United States, which were among the largest in North American history, despite occurring far from a plate boundary. Secondary effects of earthquakes. The shaking itself is destructive, but earthquakes often trigger dangerous secondary effects. One of the most devastating is the tsunami, a series of massive sea waves generated when an underwater earthquake displaces a large volume of water. The 2004 Indian Ocean tsunami and the 2011 Tohoku tsunami in Japan were both caused by powerful offshore quakes. Other secondary effects include landslides, liquefaction, when saturated soil temporarily behaves like a liquid, ground fissures, fires from ruptured gas lines, and aftershocks that can damage already weakened structures. These cascading hazards often cause more casualties and damage than the initial shaking itself, which is why earthquake preparedness also involves planning for these related disasters. Predicting and preparing for earthquakes. Unlike weather events, earthquakes cannot be predicted with exact timing. Scientists can identify areas at high risk and calculate the probability of a major quake occurring over decades or centuries, but they cannot say precisely when it will strike. Early warning systems are an important development. In countries like Japan, networks of sensors can detect the first arriving P waves and send alerts to phones, trains, and power plants seconds before the stronger S waves and surface waves arrive. Even a few seconds of warning can give people time to take cover or shut down critical equipment. Preparation also involves earthquake-resistant building codes, public education, emergency drills, and planning for rapid response. Regions with strong codes and well-rehearsed emergency plans tend to suffer far fewer casualties and recover more quickly after major events. The future of earthquake science advances in technology and data analysis are giving scientists new tools to understand earthquakes better. High-precision GPS stations now track tiny movements of the Earth's crust in real time, helping to identify where stress is building up. Artificial intelligence is being used to sift through massive amounts of seismic data to detect patterns that might signal an impending quake. Deep drilling projects at fault zones, like those along the San Andreas Fault, aim to study the conditions miles underground where quakes begin. This research could one day lead to better short-term forecasting. While we may never be able to predict the exact timing of earthquakes, our growing understanding of their mechanics offers hope for more effective preparation and risk reduction.